Okay, hi. So I'm Satyarth. I work at GO-JEK, and I work in the platform team over there. So I'll be talking about coroutines in Android and Kotlin. I'm sorry, you're going to have to see this view. Net is not working, so part of my notes are going to cover around over here. Just bear with me. So coroutines is, I think, a 2017 product. It came out with Kotlin initially, and I'm just going to try selling to you how we can actually use this on Android, and if you think this is a valid use case for yourselves, you can go ahead with using this. It helps a lot. So let's start with the direct style of programming. I mean, there's really not much to explain here. What direct style means is you specifically say that what you want to fetch, you get a response for that, that is used in the next value. So I'm trying to get an image for a user. I get it from the username, so I fetch it from the image URL. That returns me an image URL. I use that to get an image, and then finally I get to set the image on the profile. This is clear. There's nothing to explain over here. Now, my only question is how many of you think that this is going to work on Android, right? So I have the network thread on the first one. I need to perform some API call over there. I'll then again perform another API call when I fetch the image, and the third time when I try to set the image without changing thread, I'm going to crash. It's because I haven't changed my threads yet. So this is essentially, and more than that, you also need to see none of this is actually synchronous. I cannot run this on the main thread since I'll get a network on main thread exception. So all of these are asynchronous calls which we do. Then we provide various patterns to get the response back so that you can take it to the next step. What you need to concentrate over here is when you see, like, for example, the get user image URL is where you're getting your username, right? Sorry, you're passing username to get an image URL. Now, this image URL is what is used in the next part of the request. So the second, if you look at the second and third line, those actually qualify a continuation. What that means is that you're continuing your sequence of instructions from the first step, take that input, and then pass it to the second, and so on and so forth. If we have to achieve this in a normal way that we do right now, we follow something called continuation passing style. You're going to read this and say, I mean, this is callbacks. I did not use the word callbacks because everyone will start rolling their eyes like callbacks. We have dealt with that enough in our lives. Don't want to go there again. So over here, I pass a callback to get user image URL. That callback returns me an image URL when I get it. The next step returns me the image for the image URL, and then I set that to the profile. This is how we essentially deal with any asynchronous functions or methods that we need to call on Android right now. Okay. So Kotlin coroutines lets you go ahead with the direct style of programming, at the same time providing you this mechanism of waiting or suspending at particular points of your functional sequence. What happens over here is that I say get user image URL. Now, Kotlin or the compiler knows that this function is going to take time and it's going to execute on a separate thread. So it prematurely returns this function from here. While this is running on one particular coroutine, my main thread, where I would have actually started this, is free to continue moving on. So once that result comes back, then I can go to the next method for getting image. Again, I'm going to take X amount of time. Again, I can go back to the main thread, so nothing is blocked for me. Any user interactions can proceed as is. And finally, I can set the image to the profile view, which again, I have to switch threads again, right? So when I talk here. This is, now if you compare this, right? So how this actually works inherently is the continuation interface. How many of you have, okay, I should have asked this first. How many of you have played around, heard of coroutines, anything? Quite a fair number. So in coroutines is essentially divided into two sections. You have the standard library, which contains things like the continuation interface, the basic coroutine implementation, interceptors, etc. And everything that we have used, the async, launch, run blocking, all of this is a part of the Kotlin X.coroutines library, which deals with building upon these basic blocks which are provided in the standard library to make it better for us to use. The continuation interface contains three things. We have coroutine context. It's not like any other contexts that we have dealt with. It's not that scary, not that bad, very simple, straightforward, and most of the time you won't even have to deal with it. You have resume, so it's essentially the same callback mechanism. When you resume with the actual value which you were waiting for, and resume with exception is if an exception occurs on the other thread because of which you resume data. So again, now this, I'm just showing you the code again. This code is essentially backed by the continuation interface which reaches this. So what does the Kotlin compiler actually do between these two steps, right? Which makes it easy to transform this particular code to an actual continuation callback mechanism. If I were to actually decompile this code and compile it back once it comes from the APK, I would end up with something like this. What's happening over here is that the continuation which he provided, Kotlin converts that to a, okay, so we have suspend, right? So if you see the original function, we have suspend mentioned over there, and we say display user image with a string. What the suspend keyword essentially tells the compiler is to add an extra parameter to the function called continuation. Now, continuation is responsible for managing all the state. So it deals with identifying where to suspend the next function, when do I return, and basically what value I've expected from the previous function, how do I resume, etc. So over here, the continuation provides, I've labeled it as SM, which is essentially a state machine. So as soon as it enters this particular code, it first checks if there is an existing continuation. If that does not exist, it creates one, and it provides that, and it specifies at this, right? So this is basically a switch case, and this code is kind of decorated with a lot of intrinsics check, resume, etc., but it comes down to this, the basic gist of it. So you specify the label, which says that where it's going to go next, at what state it currently is, and then it triggers the first function. If the first function is also a suspend function, so that also takes the same continuation, because all this is happening sequentially, and in that function, if that suspends, because that's going to another thread to perform your network call, the function, this particular function can automatically return from here. The continuation knows now that it's waiting on another function and it's expecting value from there. So you can just proceed, this returns back to your main thread and you continue. And the next time you actually have a value from the first function, this continuation handles it with the dispatcher. I'll get to the dispatcher part, and provides it the value to be used in the next switch case, which is case 1. That's essentially a second statement where you received your variable, which was the string. It sets variables and data accordingly and then moves on and so forth. So this essentially is how writing a suspension function transforms onto the JVM or Java code when you finally use it. Cool. So we saw the continuation passing style. Now, if I were to point out a basic difference between this and the previous one, there's really not much. Both of them are callbacks. The one biggest difference is that over here, you're currently using 3 closures, and you're specifically and explicitly passing the value ahead, which would be used. When you use the continuation interface, or essentially you write code which is sequential that converts to this, you're using the same closure, and everything is managed by the state machine over here, which identifies which step you're supposed to go for next. So let's talk about coroutines on Android. Now, when it comes to Android and somebody tries to tell me like, okay, this is the new framework, this works brilliantly. So I have a set of questions essentially which goes like, will this work on it? And I mean, whenever you go and try selling a new framework to someone, they always go, will it support this? This is the big problem in Android. So I'm going to talk about 4 of these problems which we actually face regularly and how coroutines can help us solve that. The first one is multi-threading. So we cannot do, like, the main thread is not yours to use. It's only for receiving input from the user, doing whatever you want in the background, and then returning that particular output or publishing the result, the final result, to the main thread. You have to switch between multiple threads over here. Right now, how we deal with it is specifying the schedulers. We move to another thread, perform a function, then come back to the same thread. Then we check the main looper, because obviously you can't get access of the main thread whenever you feel like. You post an event to the main thread, which later sets the value whenever that handler is deemed postable. The second problem you have to deal with is lifecycle management. Again, how the user uses the app is again not under your control. So you're going to have to deal with canceling a particular task if you've got a long background running process. Maybe when you open a screen, you want to start the particular task. All these need to be hooked onto the life cycle of a typical activity so that you can essentially not return callbacks when your activity is not present over there. I mean, don't want to go back to checking if view is null again. Error handling. So if you ever error on the main thread, it's going to crash. You instead handle errors on other threads. And I mean, it's very easy to say that errors will not happen. We have written this kind of code, but you have some scenarios where errors are valid. Maybe an IO connection failure, maybe an HTTP failure. All of these are valid errors which need handling. You want to handle these errors and show an appropriate UI, right, on these. Event buffering. So you have a pull to refresh button, which is backed by an API call. Now, assuming the API call takes time, users are fidgety. They're going to start from that particular screen, start the API call, roam around the app, come back, trigger the refresh API 5-6 times more, and then wait to see if something happens, then close the app. And you essentially have sequenced 6 API calls which need to occur when all the user wanted to do was just refresh the screen once. It could be multiple clicks. You could have deal with multiple click events which happen over there. You want to consume only one, finish that off, and then maybe consider the other before actually triggering everything at the same time. So let's talk about multi-threading initially. We have the same method, the display user image. Right now, I've essentially written the threads which it would go by the sides. So you want it to start on the UI thread. The image URL is fetched on a network thread. You get the image again after getting the URL on another network thread. And just for funsies, I've added even a save image to disk, where you want to use a disk IO optimized thread. This particular thread pool where you're going to say that this is used for blocking disk operations, and this is what I'm going to use. And finally, you want to set the image to the UI thread. Right? Now, all of this is thread jumping, and you're switching between these threads continuously. So how would you achieve this with coroutines right now? To understand this, you'll essentially have to see what coroutine builders are and how they function. They are building blocks, as in they are part of the Kotlin X coroutine library, so they help you specify coroutines in the manner of specifying where you want it to start, on which thread it would occur, those sort of solutions. This is the most commonly used coroutine builder. It's launch. It specifies the context. The coroutine context over here is defined as the default dispatcher. Dispatcher is essentially like the executors. It takes the threads. It takes a coroutine and specifies on which set of threads it can be dispatched or executed. You have the start parameter. Over here, it's default. So what default says is whenever the dispatcher can dispatch that particular coroutine, it starts after that. You can have something like lazy. What lazy specifies is I would not start this coroutine unless and until someone asks me for that particular result. You have unconfined. Unconfined indicates that just start it immediately. I'm not specifying which dispatcher, which thread. As soon as this part of the code executes, just start the execution of it. We have parent, which is the job. I'll come there soon. And the completion handler, which behaves like as soon as this particular coroutine completes, if you want to do any cleanup functionality, all of that can be done in the completion handler. So again, all of these are optional apart from the block. That's the code you want to execute. So the block can't be optional over here. They have a couple of builders, which the coroutine library provides you. There's a nice blog post by Dmitro Danlik on Android coroutine recipes, which shows you how you could use multiple contexts, your values, and how they would actually behave when you specify which dispatcher you're using. Launch returns a job. The way the coroutine library defines the job is like it's something which can be cancelled and which will eventually complete. We have async, which returns a deferred, which is similar to the promise, which we're used to. You can await on it, you can cancel it, and those sort of properties. And a difference would be that when async always takes it to a new coroutine context. So if that ever errors, that does not block your main thread or cause any exceptions on whichever thread you essentially started these coroutines. What run blocking does is it enforces that you're expecting this value to come back. So run blocking is something you'll never end up using in your main code, but it's often how you would end up running tests for most of these. Okay, so let's say how do we use these with the functions we had earlier. I'm calling display user image using a username. This is happening from the main thread. I'm launching it from there. And I want to get the image URL. Over here, I can specify something like with context. Now, with context is not exactly a builder, but what it does is it'll take my particular coroutine and switch the dispatcher context. So even though I started the coroutine at the first step from the main thread, by saying with context, I can switch it to a background thread on network IO where I can perform my particular network call. Once that is completed, all I have to do is return from this particular function with that network result. And from there, I can move to the next step, which is getting the image, right? So in get image, I again go back to the background thread, and I retrieve the image based on that particular URL. Both of these are happening on the network threads. So coroutines are lightweight. I mean, what they say a lot is that you can create 100,000 coroutines without any problem. So instead of having a with context and having only one launch and continuously switching the context, you could also keep having asyncs or maybe start new coroutines. Instead, I would prefer this because it gives me a better approach for cancellation in a while. You want to save the image to disk. Over here, again, I'm specifying the context as the disk IO. I switch to the disk threads so that I can save the particular image. And finally, I set the image to the view. Over here, I can switch back to the UI context. The UI, which is mentioned here, is, again, so how coroutines works is you have the coroutine X library, and then you have an Android library on top of that, which provides you the UI context. It's a dispatcher which caters to the main handler thread. It's just, all of you have used the post runnable to post things to the main thread. This is essentially that in a coroutine manner. So with this UI dispatcher, you can set anything to the UI thread. This posts it to the particular UI thread and sets the image. One thing you can do over here is when you specify save image to disk, since you already have the image, you could do that simultaneously while setting the image to the profile view. And maybe when you're saving the image to the disk, you're not really interested in canceling it. Even if a user moves elsewhere, you can just continue saving the image. It's not blocking the user. It's not a user-facing operation. So instead of using with context, you could switch it to async. Async will schedule that particular coroutine. Now this creates a new coroutine. It will schedule that particular coroutine to execute on a different dispatcher as a specified here disk IO. The result is a deferred object, which I can either await, and that makes my thread blocking, or I can cancel it if I'm not interested in that. Or, I mean, if I'm not interested in the result, I can just ignore it. If I really want to cancel it, it gives me a cancellation primitive. So, lifecycle awareness, which is how do you cancel these things? Essentially, how do you start it? How do you cancel it? Those are the things you're worried about. So, you have job, or rather, when you launch a particular coroutine, what it returns is a job. A job is, like I mentioned earlier, it's essentially something which can be started or cancelled and will eventually complete. You can specify start if you want to delay the start of this particular job. If you do that, you'll have to specify the start parameter for this particular job as lazy. Or by default, it just dispatches whenever the particular dispatcher is available. You can cancel that job. When you cancel that job, cancel is non-suspending. So cancel returns immediately. There's a reason for that. So then you can say cancel and join, like how you would join multiple threads in a process. Similarly, you can join all the jobs which are associated with this particular job. Similar to the job and launch, you have deferred, which comes from async. You can deferred.await, which if you specify lazy, when you say deferred.await, that's when that coroutine is particularly triggered and wait for the result. You can have deferred.cancel, which then handles, you can cancel that particular coroutine before you want the result back or you're not interested. If you do not do anything with the deferred, that's also okay because it really does not affect any of the, I mean, it's essentially an object which is not, even if it errors out, it's not going to affect the current thread you're on. Cancellation is cooperative. What this means is that if I have a particular parent thread or parent job, and have multiple child jobs associated with it. So I can merely ask the child jobs to cancel. They need to actually cater to that particular cancellation. They would receive a cancellation exception, and but it's not necessary, like it's not a thread interrupt. Those things will not actually cancel because you really can't ask any process to cancel immediately. It's up to the process to decide that. Okay, so this is essentially another coroutine builder, which is a suspend cancelable coroutine. What this provides you is a hook onto the continuation that is within it. Is active is a parameter of the continuation, which lets you know if a particular task is right now cancelled or it's running. So if I were to cancel this particular coroutine, is active would become false, which lets me move out of the loop whenever. I can even install a cancellation listener, which is the invoke on cancellation, where you can do cleanup or perform extra activity once you want to cancel the coroutine. So the parent-child job hierarchy, we spoke about the parent over there. So what parent does is you can specify a job to which this also would return you a deferred, which in the end is a job. So you can specify the parent over here to which this child job would be attached. This gives me many ways to do interesting things over here, but one of the main cases you can concentrate on is that parent, canceling the parent essentially cancels all the children associated with it, right? So if I actually have save image to disk async, I can specify, like this was the async coroutine we had earlier, I can specify coroutine context, which specifies the parent context over here. And when I cancel the parent, I would essentially get a cancellation call over here too. So also coroutine deals with on completion in a weird manner. So on completion is called on cancellation and even on actual completion. Whenever it's called with actually a completed, with a cancellation, you receive a throwable over there, which lets you identify why it was cancelled. They also suggest that you should not error out a failure when you receive a cancellation, because that's not really something, an error scenario. It was cancelled by the parent, and it would kind of spoil your stack trace, explaining why this ended. So it's much better to receive or accept a cancellation exception because of which you want to do something, or I mean, you essentially take the cancellation exception and then realize that you're cancelled. You do not return the stack trace or the error over there. Okay, so while this specifies the coroutine context, and I'll be taking the value over here, what this also does is it changes my async context to the coroutine context. So if this was running on the UI thread, and I then call an async, the coroutine context specified here, the dispatcher would again be the UI thread. So instead, if I want to specify that this needs to run on the disk.io thread, at the same time have a parent associated with it so that I can cancel it when I feel like, that would be by specifying the parent parameter explicitly. So again, this follows the same process. Now you canceling the parent job will cancel all the child jobs with it. So how would you use this in your activity? The coroutine documentation or the APIs, I won't say documentation, they have a lot of examples where they show actually how to use these things. So what they suggest is that you make any lifecycle holder have a job holder interface, right? So you specify a job for a particular activity and you keep adding whatever coroutines you create to that particular job or specifying that context. And finally, when you're done, you can just cancel that particular job, which will cancel everything associated with it. So there's a very neat way of integrating this with the Android architecture lifecycle components. There's another article by Simple Asynchronous Loading with Kotlin Coroutines by Eric Hellman. This was even a talk which he gave. So you essentially take the architecture components, link that with the activity, and provide a lifecycle delegate observers for these coroutines. So whenever the activity resumes, closes, starts, etc., you can cancel the coroutines accordingly. Again, you can have cancellation for coroutines, and cancellation, pretty much everything on the JVM is cancelable. So if you want to specify a particular task as non-cancelable, that's also allowed. And you know that's a background running task which does not affect a user or does not cause any problems in any way. The way to do that is when you're specifying your with context, you specify non-cancelable instead of any of the other contexts which are available, right? So error handling. And what happens over here is that you want to fetch an error, but okay, so you're essentially getting your particular errors and you want to make sure that this does not affect the main thread. So How coroutines go about it is you have the continuation has the resume with exception. So it throws the exception back to whichever calling thread was over there. That can be called in a particular try-catch manner. It deals with like how you would deal with an exception like this. Another interesting way to do this would be you can specify a coroutine exception handler. Now, this is useful if you specify a particular pool of threads and you say that this particular threads, it's okay if it errors. You do not want these particular errors to affect anything else so that everything else can execute as is. A nice use case we had for this was when we were tracking analytics, right? So if people make mistakes or null pointers, etc., while tracking analytics, it's okay for that particular case to fail. By enclosing it in this particular block, you can essentially call that block, have it fail, and not affect the rest of the UX flow. It's kind of stupid if you have to block a user because, or fail whatever user is trying to do because you could not send the analytics for that particular event. Cool. Okay. So event buffering. Event buffering over here, it's how would you handle clicks when you actually deal with coroutines. Maybe you could, essentially, if you perform click every time, we have all used a debounce listener. Similarly, it could be if you were polling for a particular API, you want to make sure that you poll it at a particular interval. Then if you have asked for location updates and you cannot process those location updates as fast as you're doing, so you can buffer those particular events. This is how we always end up coding because, I mean, people can click a lot. This is where actors come into picture. Actors is another coroutine builder. You specify your clicker pool. A clicker pool is essentially another thread context, which I've specified for passing the events from my main thread to the background thread where I would do these details. So an actor is essentially, it's a coroutine with a state, which you can specify, and it has a channel where it can talk to other coroutines and receive messages. So you have a fetch profile actor, and I can send a particular message to it. It could be anything. If it's a multiple click, you can send multiple events. Right now, I'm just sending one since I'm only indicating a click. So whenever the channel receives a particular message, you can then trigger whatever API call or sequence of instructions you have after that. When you say send and you specify the value, you're essentially, again, sequentially adding the events continuously. So every time I click this, it's going to provide an event to the channel, and that would trigger multiple times my display user image. Instead, I could change it to offer. What offer would do is it'll try to offer that particular channel a message, and if it is currently in execution, it would currently ignore this particular message and wait for the next one. Similarly to the rest of the coroutine builders, actors are defined with all the default parameters you'd expect in a coroutine. You also have capacity, which specifies the maximum buffer capacity of its channels. So at max, it could maybe, if you set this to 1, so there can be only one pending message on this channel, and it'll ignore everything else which is sent after that. Also notice you have the parent mentioned over here. So if this was attached to your click listeners and it's on an activity, you can again cancel that particular parent job, which would also cancel the entire stream of events which would trigger from a click listener. Okay. So this essentially covers the 4 points I had, which was, these are the 4 problems I think we have come across commonly in Android, and coroutines can help you solve those particular ones. Then you also have situations, I mean, I'm not being naive. There are a lot of other problems where you have to deal with when it comes to asynchronous programming on Android. So you can deal with those problems. They're kind of more involved solutions. A lot of them require changes in the library right now. So coroutines itself is a very experimental library right now. I think it's at 0.23. And the APIs change fast. So it changes every, like I think something which I saw about 2 months ago, all the articles, blogs, etc., they have all changed to something else now. And you'll be searching for something. They have a lot of replicated values. What they do ensure is that they'll maintain backward compatibility. So if you're using something, that will continue to work. You don't have to worry about dealing, or rather, if you upgrade, you have to migrate all your code. Those sort of problems don't come up. Where do we have? Okay, so okay, this ends it. More of the references, you have the Kotlin coroutines guide, which is the entire, pretty much an entire GitHub repo, which is dedicated to explaining coroutines. What I like about it is most of it are examples. They take particular use cases and they try to solve that with coroutines. So it's a very practical, hands-on approach to it. You have the coroutines API documentation, which is a part of the keep repo in Kotlin. So over there, they specify how they're building the coroutines library. Kotlin X coroutines is where the source code for this currently lies. And like I mentioned earlier, this is in its very infancy state right now. There's a lot of discussion which goes around the coroutines library, and a lot of it is user-driven. So this would be a good time to actually use this particular library, come out with problems you have in that or things you want to solve, and actually contribute to the development of this, since this would pretty much help you shape how you'd use this library moving on. Okay, I think I'm done. So this was short. Any questions regarding this?
Yeah, we definitely have time for questions.
Hi. Thank you for the presentation, first of all. I actually want to know, I've been following coroutines from the time it has been launched, and I always, like whatever I've read, I always think that it can be a substitute for RX Java, but I not that bold, like I didn't get that much confidence to change my RX code and try it using coroutines. So I want to know, have you tried it, and what, if you have, what is your experience?
I was actually happy I managed to make it through the entire presentation without mentioning RX Java. So it's not a substitute. The thing is, right now we are comparing apples and oranges. RX Java has a multitude of operators. It has a lot of functionality which coroutines as such right now will not be able to provide. Coroutines can be used, like coroutines also has an RX Java, I won't call it wrapper, but it's essentially a library extension where these two can supplement each other. So it all comes down to what use cases you have, right? So if you're using RX Java right now to make API calls, switch threads, come back and do something, then maybe this would solve that particular use case. If you use multicast, if you use multiple sources of data where you're concatenating everything and you're totally into how you use operators, then stick to RX Java, because that does not work here right now. And if you're comfortable with RX Java, I don't see why you would want to shift. Because if it's taken care, then sure, you don't just shift to it because it's new, right? So if it's actually solving your particular problem, you can, but otherwise, no. Does that answer your question?
So compared to RX Java, when you talk about network operations and performing API calls and getting the data back, so is there any comparison, or like RX Java is better performance-wise, or like coroutines is better performance-wise?
So you can check the GitHub repo for coroutines. They have benchmarks mentioned over there, and I think there are a lot of blog posts which talk about benchmarks around this. But I mean, my question is more of what exactly are you doing which requires that much performance? So, I mean, even if you're making network calls, you can't be making about 20,000 calls a second. So I'm quite sure it'll work equally well in both the cases for you. Anything else?
Any other questions? Anyone else? Cool.